things like that. So it's good to know those sort of operating standards. And then testing standards. So when I said we run verification validation tests at the end, a lot of industries, especially regulated industries, have testing standards that you have to do a certain set of tests on your device. So you want to be able to include all those things up front when you think about your specifications, right? So any standards that would apply to you, you want to know them in the end. So I know a couple of you are doing construction projects, like the Ecuador team, and there most certainly are construction standards, right? And you have to follow those standards. And so when you're designing your device in the beginning, you want to make sure you comply to all of those. And there are a lot of different standards organizations. Usually there's one big one for each sort of discipline that you might be in, but some have a bunch of different ones. So as an example, I was on an ASME committee for a number of years, working on verification validation of finite element analysis. So when we do a model for medical devices. So those kind of standards tend to be behind the technology curve. And the reason for that is they're usually composed of volunteers who meet twice a year at best. And so it takes them a long time to develop agreement and standardization as to what you should do. And by the time they get them done, years have passed and the technology has moved on a little bit. So they're usually behind a little bit, but they're still helpful guides. My battery pack is falling apart. So in the sort of big picture of design, specification is the last thing that happens before you start creating conceptual designs, right? So if you are a perfectly disciplined engineer, you hear a problem statement, I need this thing, and you go and you do all this research about it, you create your sort of project identification phase where you come up with the user needs, you go and interview users, you make observations about what people are doing, you get this great list of user needs, you then take all your user needs, you make specifications from those that are quantifiable, and then your team sits down and you start to brainstorm, come up with what are our concepts to solve this problem. Does that sound realistic to anybody? Yeah? You guys are awesome. There's no way, right? The minute I hear a problem statement, I'm not doing all that other work right away. I immediately think of 3 solutions, right? That's how we work. We hear a problem, we immediately become creative. We start to problem solve. That's okay. You don't have to suppress that. But as a disciplined engineer, you're going to write those ideas down. You're going to capture those ideas. You're going to stare at the ceiling. You guys are so nervous. Settle down. He was in my collar. He didn't sting me. You're okay. So you're going to go through and you're going to come up with those ideas. That's okay. Don't suppress it, but hold on to them and be disciplined enough to go through this process so that when you get to that brainstorming phase, you actually fully understand the project. You understand what all the things that you have to satisfy are, and you'll do a lot better job of managing big projects, okay? So especially if you have a project that has a lot of components and parts that have to work together, if you come up with all those ideas in the beginning before you work through this process, you'll end up with a bunch of mismatched parts that don't go together, right? So work through this, think about it. So yeah, this is not realistic. So one thing I wanted to touch on, just real briefly, have any of you read Zen and the Art of Motorcycle Maintenance? Have a couple of times? You should. It's a really good book. It was recommended to me by my thermo professor when I went to school here, and I thought he was crazy. I'd never read a book like that. I've read it a couple of times. It's a really great book for anyone who's going to be in Zen and the Art of Motorcycle Maintenance. So it's sort of Buddhism for engineers, I guess, lack of a better term, but it's a good worldview. Did you get him? Nice. Okay. So, all right, you guys can breathe easy now. This beast has been slayed. But he describes the scientific method. So he's talking about working on a motorcycle, right? Motorcycle maintenance part of the book. He's talking about working on a motorcycle, and he says, you know, in the beginning, when you have a problem, you just look for the obvious solutions. But whenever you get to something that you can't figure out, then you can crank up the sort of scientific method on it. And you can go through, you can create a hypothesis, work through it, and you can go through that long form process of finding out what's wrong, right? And by doing that, you kind of crank up this invincible machine, right? Nothing can defeat the scientific process if you work through it the right way, right? It'll take you longer, it's sort of slow and laborious, but you get there. And I think the engineering method is very similar to that, okay? There are a lot of problems you'll solve, things that you'll make, without sort of going through this whole design process from the start to finish. And those easy or kind of quick solutions are fine. But when you get into the kind of problems like you have here, if they were easy, they'd already be done, okay? That's when you want to crank up that full engineering design method. That's when you really want to think about all of these steps of the process and going through it methodically and slowly so that you don't make mistakes, right? So you're not going to just kind of come up with a quick hack fix to put a man on the moon, right? And we all see Neil out front, okay? That takes a lot of planning and effort. It takes a lot of iteration, right? So they didn't start at the beginning, think, how do we put a man on the moon, build one spaceship and send it. First you send up a dog, right? Because you don't want to go that one step. And before you ever got to getting the dog up, you were running tests on the ground, you're running simulations, you're doing those things, right? So I've lost my batteries. You want to work through that whole thing. So the engineering method, while it's not always the most fun way to go about solving a problem or the fastest, it is very effective at those big grand challenges. Okay, so when you stop and you look at like the grand challenges before us in the world, if you look at Engineer of 2020, things like that, there's lists of grand challenges out there. All of those challenges are solvable by engineers like you or by designers like you, people in design teams if you're not an engineer, by cranking up this method, right? You work through it slowly, laboriously, but with intensity and dedication through the process, and it can't be stopped. So a little plug for real engineering there. So another thing to think about in the process of coming up with specifications is this concept of emergent design, okay? So if you look at the map on the right up here, I think this will take me to it. No, not yet. Okay, we'll go map on the left first. How about that? So this is an interstate map of the United States, for those of you who aren't familiar with this. So if you were wanting to plan a trip from St. Louis to Oregon across this map, you could do that pretty well in the beginning, right? You could sit down, you could pick out your route. So this is what people did before Google Maps, or before MapQuest if you're a little older than that. We would sit down with a map like this and we'd actually pick a route to get where we're going, okay, through these roads. And you could come up with a pretty good prediction of how many miles you're going to go, how much we're going to spend on gas along the way, how long it would take. So if you think of your project planning at the beginning like this is kind of what you're taught, right? You sit down at the beginning and you should figure out all of the details, come up with a perfect plan. You'll know what it costs, how long it takes, all those details, right? But that's not really how it works for you guys because you're novice engineers. And when you get out and you get into the world and you're doing really difficult problems, even if you're an experienced engineer, you don't know all of these details, right? But if you think of what this map looked like at the time of Lewis and Clark when they were trying to get to Oregon, okay? They were trying to find the Northwest Passage. This was the map of the United States, okay? This is all that they knew. So if you were looking at this map and you wanted to plan your trip to Oregon, you would have a really hard time figuring out how long it's going to take, what supplies you should bring along, how much it's going to cost, okay? Because you have no idea what is west of the Mississippi in this, right? It's just a big green nothing, okay? Those river lines are all pretty well wrong to the left, okay? They had no idea where they were going or what trouble they would get into along the way. And this is what design is like when you're a novice engineer or you're doing something that no one's ever done before, right? You don't know where you're going, and that's okay, all right? So a lot of times your teachers will expect you to figure it all out in the beginning like you have that big roadmap because maybe they've been working on similar problems for a long time, right? But you haven't. So this is the kind of worldview you look at. What's important is that you make your best guess because you've got to head out on that journey in the beginning, right? So Lewis and Clark had to go and figure out how much rice and how many barrels of whiskey and things like that they needed to bring with them on their trip. It's important bartering material. So they had to figure that all out and they had to make their best estimates, right? And as they went along, they did things like trading and hunting to try and figure it out. And so that's kind of the path that you guys are in. So if you think about, the design process, we've got it back here somewhere. You start out in project identification and you kind of start to figure out what the heck this project is all about. Like, what do these people really need? And then you get into specification development and you start to try and pin down exactly how you're going to go through that path, right? And then you get into conceptual design. That's the most fun part that we end up getting stuck in forever because it's fun, right? You got to be creative. You got to come up with prototypes. And then as you move forward into that detailed design, you'll go back to specification development again because you realize you missed things, you did something wrong, and you'll cycle through that. And each time you do it, your map gets a little bit more detailed, right? You start to understand what this project needs, what all the steps along the way are, and then you can get to the point where you get to the detailed design, and then you've got the full interstate map, right? A detailed design time, you say, I know exactly what I'm doing, here's how we're going to do it, here's how we're going to manufacture everything, and that's the steps you go through. So that's emergent design. So if you have advisors that are like, why are you guys not able to plan this out from A to B? Tell them that you're working through emergent design. That'll calm them down a little bit. They'll have no idea what you're talking about, but you will. Okay, so I want to go into functional decomposition as a tool for coming up with specifications again. And it's kind of a cool tool for coming up with user needs, but you can assign details to these. So have any of you done a functional decomposition before? A little bit? Okay. So this is just another tool. So you can work through what are my functional requirements, my interface requirements, what are my performance requirements. And then you could think about it, and that's kind of going through those categories. And then you can come back and think about it this way by function, and then compile those lists together, because maybe you'll see some things that you missed. And the point of these is just to give you a sort of systematic framework for going about finding specifications. So I sat in a lot of meetings as an engineer where we'd have everyone on our design team in a room, and we would just be like spitballing, shouting out specifications, and we'd come up with a pretty good list when I could keep people awake and engaged, because it's kind of a boring thing to do. Think of everything this needs to do. But if you have a systematic approach, it helps a lot to be able to go through them and say, all right, here's all the things this needs to do, and then we can break each one of those things into its components and break each one of those things into its components until we get down to a level that we feel comfortable with. So at a first level, if I say I'm going to design a coffee maker, right? The purpose is to make coffee, and I can break that down into sort of its functions. So first function might be it needs to be able to store and heat water, right? I probably want hot coffee. You're going to have to use water. I'll need to store and grind the coffee beans themselves, right? So I'm going to have to do that. I'm going to actually do the process of brewing, so pouring the water over is a function I'll need to have. And then I'll need to keep the coffee warm, right? So that's a fourth function. So that's kind of the first level. And then you could break each of these down. Okay, I need to store water, so I need to have a reservoir. As I want to get into specification, I want a reservoir that can hold 12 cups of water, right? I'm doing a 12-cup coffee maker. And I want it to be able to heat to 190 degrees Fahrenheit, right? So as I start to look into each of those steps, I'm going to break them down into more and more detail and start to apply numbers to them that I can say yes or no, it does or doesn't do this. Same thing with I need to store 2 pounds of coffee, right? This would be a pretty good storage unit. I need to grind the right amount of coffee for 12 cups or 8 cups or 6 cups, however much I'm doing. And then you can say, how much coffee is that? That's 4 tablespoons or it's 12 tablespoons. See how much coffee it's going to be. And I'm going to brew it. So I'm going to say I want to be able to pour all of the water over the coffee beans within 8 minutes, right? There's some specification there. And then I'm going to keep coffee warm. So I'll say I want to be able to keep my coffee hot in the pot for 2 hours. Up to at least 120 degrees, right? So you start to apply numbers to those things. Does that make sense? Okay. So while you go through all those, you could get to the end and you could say, is this a functional requirement? Is it an interface requirement? But that's not really what you're worried about at this point. You're just looking at it from a breakdown of functions, okay? So each of those you could get down to saying, okay, I'm going to store water. How does the water get into the thing? That means I need to have an opening where a user can pour water in, and then I'm starting to think about interfaces. Right, so as you keep breaking it down, you can get there. So the last thing I want to show you is just an example of what the documentation of this could look like. I'm going to hide this one because I think we don't really need it. See if we can get all this on the screen. That's close enough. So the main ones you're going to look at here. So we talked a week or two ago about designing a kite, right? So we looked at user needs for a kite. So if I think about my kite project, and I put up 4 user needs, it needs to be able to fly, right? That's something my user wants it to do. It needs to be stable in flight. I should be able to control it from the ground, and it should be visually interesting. Say those are the 4 user needs that I put forward. So I enumerate those 1 through 4, okay? And then my specifications, as I want to get into, I'm calling them design inputs here. I'll call them specs. so that we're consistent. So one thing to be aware of, all the concepts we talk about within different industries have different names. As long as you understand the concept, I'm not worried about you memorizing the name, you'll know what we're talking about. So if I look at specifications, okay, I say my kite should fly as my user need. So I'm going to say if it's going to fly, then I need it to satisfy these criteria. It should be lightweight, it should have a large surface area, and I can go through and give those specific numbers, right? It needs to be less than 2 pounds. So when I get to the end, I'm going to do a verification. My verification test would be to measure the weight. Under 2 pounds, then I would be satisfied with that criteria. If I'm looking at verifying that I have a large surface area, I could do some surface area analysis, like looking at the schematic of my device and seeing what the surface area is. And I should say, all right, that should be in the range between 2 and 4 feet. If it doesn't fall inside that window, then I haven't satisfied my criteria. Okay? You can go through and go on and on about all the things you need to do to fly. But even if you meet all these specifications, you haven't proved that it flies. That's where we do a validation test. So I have my user need, corresponds to a validation test, and in this case it would be a flight test report. So I went out to the park and I flew the kite. I have evidence of that, right? So there I said, here are the things I need to satisfy for it to fly. I did those, and then my validation was, yes, it could fly, all right? That's why you write your user needs and specifications in this way at the beginning, so that when you get to the testing phase, they correspond one-to-one, and your tests aren't just whatever random thing you came up with at the end, okay? So we could continue through these. I don't think there's a need to go into much more detail on them. I think you understand the idea. So what I want from you all this week, you can email them to me. I can put my email up if you don't all have it. Anti-dust chalk. Awesome. I assume you guys know the end part. So it's just my last name, Pierce, the number 1. So I want you to write a list or a table like this with your user needs and specifications, okay? You don't have to have the verification and validation. If you want to do that, that's great. But not for the kite, for your EPICS project, okay? I'll go through all those and I'll try and get you all feedback on them sometime in the next 2 weeks, probably, by design review. How's that, okay?
Did you say there's a template for this? Or
there is a template in the OneNote notebook. So those of you using OneNote, in the design document tab, this is all kind of built out in there already. Otherwise, it's just a numbered list of user needs and then a sub-numbered list of specifications. So not too hard to recreate on your own. All right, make sense to everybody? Okay.